So I'm joined today by a special guest, Susanne Yelin, professor of physics in residence at Harvard University. Is that still accurate, in residence?
Yes, that is correct.
That wasn't a term. You're actually at the University of Connecticut as a professor as well.
Yes.
Right. Very interesting. And so your background is more in theoretical AMO. You're a fellow at the American Physical Society and a fellow at Optica, which I guess is that's almost the American Optics Society.
It is. It used to be, actually.
Used to be.
They changed the name.
And you've been doing some incredibly interesting work at Harvard. You just gave a talk earlier today here at the Simons Institute for the Theory of Computing. Can you tell us a bit about, well, first, how you made that transition from sort of the theoretical photonics to working with actually trying to make an application with a quantum computer, and then what the application is you're working with?
So it was actually much less a transition as in phase transition than you might think, because in quantum optics we were basically involved in quantum information early on.
Right.
A lot of the platforms are AMO based or quantum optics based. And a lot of the applications that we, for example, kind of use to justify what we are doing to our funding agencies and our papers, etc., was, with this great photon control, we can build quantum computer. Or here, that gives us, in principle, the possibility to do a quantum control NOT gate with atoms or something like that. So the jump wasn't all that bad. For me, the real transition was a transition from doing relatively application-oriented quantum optics to very theoretical quantum machine learning. And I had a postdoc who was interested in that. She came and she came with money elsewhere and was funded in order to do quantum machine learning. And I had a couple of people who were in my group who kind of immediately got interested and started a little bit in their own direction. And I have to say, my first exploits, I would say for the first year or so, were really highly frustrating in this direction. Because machine learning, we know that all, ChatGPT, large language models, etc. Yeah. We're talking about millions and billions and whatever.
Trillions.
Trillions of whatever.
Of whatever, yes.
Quantum machine learning, because we don't have any working quantum computers, you have to simulate everything.
Yeah.
And so we could do a quantum machine learning simulation with 6 qubits. If we went really big, we had 10 qubits.
Yeah. It's not big data.
It's not big data and nowhere close. And in addition, and that was not clear, the results are really not that great.
Yeah.
Yes, you see some learning, but it's not. Oh, wow. Okay.
Yeah.
This was the one thing. And the second thing is that in order to even get to that point, you have to already kind of, you wouldn't see that in the papers or in the talks, they always say, we tried that and this gives this great results. You try like 7.5 different models and ansatz and kind of loss functions, etc., until you hit one that actually works.
Right.
And then if you do quantum machine learning, there is this so-called Barren plateau problem where you basically, the slope of your evolution is basically, at least as far as machine precision goes, 0.
Right.
And so there is no evolution anymore. So this is the more quantum and the more entangled you go, the worse the problem that tends to be. And so my first year was like, okay, we have tried this. Now let's see where we can use this experience. And then we started to get more into analog systems, where we go away from the idea of a universal quantum computer.
Yeah.
And our first model was actually so-called quantum reservoir computer. And classically, a recurrent neural network is a network where your learning doesn't go only in one direction, but where you can basically circle back and kind of go through any nodes any number of times.
Right.
a subclass of that is the so-called reservoir computer, where the connections between the nodes inside you cannot optimize. They are fixed, and typically they are either on or off, and that's it. And the only learning that you do is basically you look at your outputs, and there is basically a filter function, which for classical typically is classical, and it's more often linear, but not necessarily. And that one you can learn on. And other than that, you just let your evolution run through the computer, and this is usually done. You have an update function. So here we get very brain-like. So every node, or every, let's call it neuron, every neuron is modified by its direct environment, namely by all the axons or connections that go in there. Plus,
and what's the physical implementation of that reservoir computing?
Exactly.
Is that photonic or?
So the first of it is really the brain.
Okay.
Then there is the classical one, and the classical is, I don't know how much classical reservoir computers there are. People just, I think, simulated it and figured this is actually a relatively stable way of learning.
Right.
For quantum, any kind of sort of analog computer that we have is very good for it. So in principle, they for me, with a background in AMO, the obvious way would be an ensemble of atoms. And these atoms have some kind of interaction. For example, like for the Rydberg arrays, if they are in the Rydberg state, they have a van der Waals interaction. But it could be also the normal cooperative interaction, which happens already in the lower. Can be anything.
Okay.
It's typically, it can be completely amorphous. That's one of the things that I really like about it. You have this basically, you can have a relatively big amorphous set of atoms of any arbitrary connectivity. You take typically a relatively small part of it and define them as input. And an equally small part of it and define them at output, and all the rest is just the computer. So because you can go round and round, you have typically quite a bit of redundancy of the way of learning. And I think that's also the big advantage. And if you go quantum, of course you have the advantage that you have all the typical, cheap quantum advantages like interference. You can have various non-commuting bases and true randomness.
Right.
And with that, we came up with a couple of simple ideas how one can use this interference to get basically fault tolerance or even automatic error correction and so on. And this turned out, of course, we could also not model particularly much bigger systems, but this was much more promising. And not only because it worked better and we didn't have to deal with something like Barren plateaus or so that just didn't show up in this case, but in addition, this promised to be much more accessible to present-day machines. The reservoir computer itself does have, as I say, fixed connections between the nodes, or now they are qubits. We can go a little bit further than that because the typical, for example, Rydberg array has global pulse control, which kind of has an effect on all of these connections, the same effect on all the connections, as long as the distances are the same.
Interesting.
But it gives you quite a bit of control, and it turns out that we showed that subsequently, if you kind of condense this down on single nodes, that you can, in principle, actually build a universal quantum computer from that.
Amazing.
And this is still work that we now I think starts the real work.
Right.
And one of my goals, for example, with that is I would like to build a machine, for example, a sensor, where the kind of ensemble that does the sensing, for example, like a ensemble optical clock, atomic clock or something like that, is actually the same that is also the quantum machine. So we use that both time as a quantum machine learner or reservoir computer as we use it as for getting the signal.
Is there some relation between what you're describing and measurement-based quantum computing? Because that's often...
No, that's different. Because measurement-based quantum computer, you need control over every single connection.
Every single one, that's right.
So you measure, then you say where you go on or where you measure next. And you have to read out every single one. In our case, the readout is, depending on what we have, usually just a projection of the output qubits on the measurement basis. And so we just get a set of zeros and ones at the end, and that's it. And then, of course, we can do learning, so we can kind of make a loss function, do a steepest descent, whatever, and then feed with a little bit different parameters back in. The different parameters will now be, of course, also how we do the pulses for these global connections.
Okay, interesting.
So and I mean, we have done a couple of other things. We also have tried to kind of optimize how one can take as much of the quantumness as is still efficiently simulable on a classical computer, do that on a classical computer and leave only the rest for quantum.
Right.
That's one direction. And this talk that I gave today is yet another direction. Here we set out and we said, okay, we want to do quantum chemistry. There has to be a way to do quantum chemistry that quantum chemists actually buy into. That was for us really the starting point.
Did you start to work on the Rydberg array device out of Lucan's lab
I'm not
before, or I mean, have you?
I mean, I knew it very well. It's half of the people with whom I collaborate. You might not know that I also happen to be married to him, so I know a lot about the Rydberg atom array. I also...
You're probably sick of hearing about it by now.
No, I'm actually not.
No, it's amazing.
And I also work a lot with the people at Quera. But that was, the kind of the obvious best thing that we had in mind. We are also talking to actually people, Markus Greiners, who has an optical lattice with fermions. So if one wants to do anything like Fermi-Hubbard model or so, and for what we do with the quantum chemistry, fermions are next. And for that, we actually will have to probably kind of mix platforms a little bit. But the way how we got to that was, we have something that fits very well, a kind of a method that fits very well on a experimental platform that is there and that's being developed at a very fast pace. We saw that people do basically reinvent the wheel of chemistry going back a couple of 100 years. And we thought there has to be a way that we really leverage what they know already. And figure out they cannot do everything yet.
No.
So they have
they wouldn't
to be
talking to you otherwise.
Exactly. They have to be there have to be some things that they are not as good at. And of course, naively as we were, Anna Krylov, who is at USC, we had kind of a little bit collaborated on something else, so she was an obvious person to talk to.
And of course, Martin had Madsen's. Martin had connection with Anna, so Anna brought in Martin. I see.
So we had the two of them, and they are both pretty open-minded towards quantum computation and so on. Nevertheless, when we asked them, so what kind of problems are hard for you to solve? The answer is typically, no, we can do everything.
Well, they are scientists. That is sort of the default answer.
I don't blame them. Why should we, idiots who don't know anything about chemistry, kind of know it better? And so it was actually, I would say, about a 2-year journey to be able to understand what they are doing and what they are good at, what they are proud of, what their questions are, etc. And similarly, to explain them what we might be able to do. We, of course, were there in the in the beggar's position, because they could do all that already. We could not. We could just say we might be able to potentially do that. And so for me, the starting point was actually not what kind of problem, but for me, one of the first things was really how can we get the input-output together such that the classical computer and the quantum computer can play together very well.
Yeah.
And this was somewhat kind of automatically solved by this very effective kind of readout that you can do this kind of, because for the Rydberg array you do these single shot measurements where you with one single kind of camera click get a projection of all qubits, and by now this is in the high hundreds, and which tells you whether this is in a 0 and a 1.
Right.
And so this can be done relatively efficiently, and this project is somewhere, it's a little bit of machine learning, but not really. It's a little bit of simulation, but not really. It's a little bit of computation, but not really. It's really kind of at the overlap of all three of them.
It sounded also like you had analog time evolution in addition to logical gates.
Yes, exactly. And our logical gates, of course, are multi-qubit gates. And this was multi-qubit gates was somehow an obvious thing to do with these Rydberg arrays, because it was clear their gates work just in proximity, but you can bring way more than 2 of these atoms into proximity.
Right.
By now, this is about 8. I think if they work towards it to try to make that higher, they will be able to make it considerably higher, especially if you go into 3D, which they don't so far.
Yeah.
And then there is, I think, this kind of going away from trying to do things purely digital and trying to say, okay, we are going back to what we know from the Reservoir computer and kind of optimize our pulses. And we now, for this particular, we have basically 4 time-dependent quantities that we can. These are the strengths of the laser, of 2 laser fields, and the detunings of both of the laser fields. All of them are with limits, fully time, you can make full time evolutions. And so by that time, we had also kind of gotten with the quantum chemists and with our trying to understand quantum chemistry papers, etc., gotten to a point where we figured, okay, now we can try to do something.
Right. And so you picked a molecule with high correlation. You were talking about high correlation.
Yes, exactly.
It's a biochemical catalyst, is that right?
Yes, exactly.
And I wasn't certain from the talk, are you simulating the whole molecule or just the manganese, like just the one set of bonds?
So the thing is that the overall kind of large scale spectrum is known. So the electronic spectrum is known.
Right.
The vibrational spectrum is known.
Right.
But a lot of the subtlety, where really the detail matters, comes from the spins, because these are large spins and they are, after all, relatively close together. This is actually an energy scale that we normally in the typical kind of whatever kind of, for example, condensed matter Hamiltonians don't necessarily get.
Right.
And so this is really, I wouldn't say this is the missing link, because people understand that already pretty well.
But you were demonstrating that at those low energy measures, you potentially are getting sort of higher fidelity simulation than you can do through classical means. Okay, that's what I was thinking.
And I mean, of course, the classical means, the thing that you do, for example, a direct diagonalization. So you assume you have a Hamiltonian, you just diagonalize it. For this molecule that is already a state space, that if you do it fully, so for example, if you take the molecular orbitals as S-basis functions, you cannot do this classically by a large margin already. What people can do still classically is probably up to perhaps a little bit bigger than water.
Right. Yeah.
So the thing is, of course, we have also limitations in resolution, etc., because our quantum computer, of course, is not error-free. So right now, the quantum computer has an error of a tenth of a percent.
Yeah.
And I mean, we do so far still simulation, but we simulated everything with this kind of tenth of a percent error rate. And then, of course, it's also the question, I mean, if you, the error bars get smaller and smaller, the more samples you take, you want to stop at some point. The examples that I showed today is also all a couple of K samples, which can be done relatively quick for the experiment. And in moderate time if you do the classical simulation.
That's really interesting. That's really interesting. I loved the way that it, I mean, I feel like we're in this stage right now when, maybe there's a growing realization that, purely NISQ approaches have kind of been, run the course, and we kind of gotten what we can get out of them. And, we all want logical qubits, and doing large numbers of fault-tolerant logical qubits is going to be very hard to do. But the way that you're approaching this is in this sort of in-between state where you're combining a variety of the strengths of the platform and avoiding some of the weaknesses of the platform.
Exactly. Thank you for, that's actually exactly where I want to be. I mean, there's, from this NISQ, there are exactly two directions. The one is really going towards fault tolerance, error correction, as full error correction. And people, I mean, the Rydberg array, they can do this now, right? The other thing is, we don't do fully error corrected, we go to fault tolerant, robust, whatever you want to call it.
Right,
and see how far we can do with that, exactly. And then, I mean, the point is right now, I think we have circuit depths that are still, I think compared to when people simulate full universal quantum computers, we are doing pretty well. But for what you would need in order to do a similar quantum chemistry calculation for a universal quantum computer, we are orders and orders and orders of magnitude away.
Right.
But we can in principle do the same thing. And we have now just a combination of various ways how to do that. The one is redundancy. The second is this optimization of the pulses that really can be tailored for exactly the system that we want to have and still be run globally on the system. And then very, very clever pre and post processing.
Right. It feels like that is always going to be the case with these use cases.
There's nothing wrong about that.
No, of course not. I mean, as we said, the even just on the face of it, the data bandwidth limitations of even a 20,000 qubit quantum computer is not trillions of bits like a classical computer is. So. They each have to be played for their strengths, is what it feels like.
Exactly.
So you mentioned, error correction being one of your next steps. You mentioned moving into dynamics, I think, of chemical reactions. And also you mentioned lithium hydride is that sort of your next?
No, so lithium hydride is of course ridiculous compared to this. So the reason why I showed this, and this, you saw this, I mean, this is a very serious spectrum with a couple of thousands of lines already. Where we actually, and I did not say that's basically our earliest, where we take the not just the spin, but also the fermionic nature into account. And in principle, it's not better than what other people who kind of do lithium hydride on the quantum computer do. But we do that now with these particular methods and just see how far what we can do. And one of the things that we want to do, which I haven't seen that much from other people, is actually calculating this kind of potential surfaces. That's what I showed for H2. That is something which we can in principle scale up as much as we want.
Yeah.
We might lose accuracy for the larger ones, but it's not that we say, okay, in 10 years we might be able to do let's say a molecule with 10 atoms.
Right.
We could do that tomorrow.
Right.
And probably the accuracy, we would have to run it a little bit longer. I also should say, so far these are all simulation results. And they have now just last month started running the first of these multi-qubit kind of analog ideas on the Whitberg machine at Harvard. That is, of course, a machine that's much in need right now. But this stuff, we will try this all out certainly before the year's out.
Amazing.
And for that machine, there is not really a difference whether we do a molecule that is like as big as the one that we showed there, this catalyst, or something that really uses every single qubit on the machine.
Amazing.
The thing is that there is a little bit of pre-processing work needed. We need to calculate the optimal pulses for certain gates.
Right.
But once we have them, we can just run them, and we run the gate for whatever 3 qubits, then we run the gate for 4 qubits, etc.
Right.
And that can be all done in parallel. And there's, as I say, I mean, as long as it fits in the present machine, there is no limitation.
Right. And is that something that your computational chemists or your quantum chemists, Martin and Anna, are excited about?
Yes,
seeing?
I think they're very excited about this. Yes.
Well, that's great. It sounds like we're going to have you back once you get those results.
Well,
thank you so much. This has been really interesting.